Welcome to Study Loop.
Okay, this is chapter 11, section problem 104. And it asks us to refer to figure 11.3 to answer these questions, and I have that right here. So this is the heating curve of water, and we can see that they labeled the different regions of this heating curve as 1, 2, 3, 4, and 5, and that relates to the different regions. So ice, and then we have the melting of ice, which is fusion. Then we have the heating of the liquid water. We have the boiling or vaporization. And then we have number 5 is the heating of the gaseous vapor. So A asks us, a sample of steam begins on the line segment labeled 5 on the graph. Okay, over here. Is heat absorbed or released in moving from the line segment labeled 5 to the line segment labeled 3? And what's the sign of the Q for that change? So in addition to the graph literally saying that heat is added, moving from left to right, which would mean that the reverse of that, moving from right to left, would mean that heat is released. We know that, when you're going down in temperature, your molecules of water are losing kinetic energy. So they have to be released, generally speaking. And what's the sign of that change? So it's going to be released. And the sign is a negative change in Q. So when we're talking about Q, that's the internal energy that those molecules have. So it's releasing that energy from inside those molecules to the solution or to the surrounding, and it's giving up its energy, and therefore it's a negative change in the Q. Okay. B, in moving from left to right along the line segment labeled 2 on the graph, heat is absorbed, which confirms our answer from A. But the temperature remains constant. Where does the heat go? Okay, so it is true that when you're melting ice, the temperature doesn't change until you have completed the conversion from solid to liquid. And that energy goes really into disrupting the stabilization provided by the crystal lattice structure. So it goes to breaking that stability provided from the solid. So this stabilization and these bonds right here, these interactions, there's a lot of energy that is conserved or saved by forming these highly organized, highly structured, structures. So in order to break that, you need to give it energy. So that's where it's going. But it's not changing the kinetic energy, the overall kinetic energy, until, overall, on average, it's been converted completely to the liquid. Okay. C, how would the graph change if it were for another substance other than water? So, most substances are going to look really close to this, where you have, 3 phases, solid, liquid, gas. If you have something that goes just from a solid to a gas, then it'll be pretty different. You just skip that liquid phase, and instead that would just be sublimation. But most substances are going to look similar to this. We're going to have 5 regimes, but the slopes are going to be different. So, if it takes more energy to heat up the liquid, per mole, then you would have a less steep slope. Most liquids actually would probably have a steeper slope than liquid water, because water has a very high specific heat. It takes a lot of energy to heat liquid water a degree Celsius, per degree Celsius. So the slopes will be different, and also probably the lengths of these plateaus will change depending on the substance. It might take more or less energy to convert it from the liquid stage to the gaseous stage, depending on the amount of energy that is stored in those bonds. So be pretty similar, but the slopes will be different, the lengths of the plateaus will be different, and also just the values generally will be different. Water water sits at this location on this graph because it melts at 0 degrees Celsius and it boils at 100 degrees Celsius. So if you're dealing with something like methanol, it'll have, or ethanol, it'll have a different melting point. It'll have a different boiling point. So the absolute values of the temperatures and of the heat being added, those will all be different. Okay, good luck studying.